Hi again, welcome everyone. So this is I'm picking up the discussion from this example problem. I thought it would be a good idea to kind of look at those adjustments of this problem. Just real quick, I'm going to go ahead and get into the slideshow mode. And then in the previous lecture, we applied these independent variable values from this table for zone 1 and then these values for zone 2 into these two models, and we estimated T1 and T2 originating and TJ and for same for the destined for zone J. So this is what the numbers we came up with. So let me write down those numbers. So T1 origin value was 15,000 trips, and I'm going to write to, and then T2 origin was equal to 22,500 trips. And then if you look at the same thing from a destination perspective, basically applying the second equation here, that was equal to 16,000. And then T2 destination was equal to 20,750 trips. And now your job was to figure out, if I add these two up trips total, if I add these two trips total origin, total trips produced, basically I add those numbers up and I get 37,500 in between those two zones. But if I look at these trips, total trips attracted was equal to, when I add these two numbers up, I only get 36,750. So there is a discrepancy. I had a total number of trips being 37,500 and total trips attracted are only 36,750. And so that's a problem because I'm applying these two models. So I need to apply a correction. And how do I apply a correction? I assume, because it's a morning peak hour trips, that means my origin model is relying on the household characteristics. So that means I could consider that to be more accurate. And once I use these numbers, I can apply the correction based on these formulas here. Okay, so 37,500 trips, and this is only 36,750 trips. So I'm going to try to adjust my destinations because I assume my origins are more accurate. So in that scenario, I can say, I can say that my T1 prime as a destination, how many trips zone 1 will be equal to, because I'm trying to adjust that. So T1 prime as a destination will be equal to TJ, my original value for that destination. For T1, it was 16,000. Okay. I'm applying this formula. Summation of capital TI based on the origin, that was 37,500. And I divide that number by 36,750, which is summation of all the TJs. So I apply this value, and whatever that comes out to be, I'll let you do the arithmetic. And for T2 prime, the number adjusted would be same thing. It'll be 20,750 times 37,500 divided by 36,750. Now the beauty of this is when I sort of add these two trips up, now my trips are going to add up to 37,500, which is also the sum of my originating trips. So that's how we apply the correction, and you can estimate this value. But when you add up T1 prime and T2 prime in this scenario, then they will start adding up to 37,500 again. I hope you're able to see that. And that's why we do the normalization, so that we can get more accurate estimate, because we do think that the home-based trips are more accurate typically, because they are based on the detailed census data. Employment data is supposed to be more off in nature, or more suspect in nature. Okay. Actually, there is another way of figure out the drawing here. There is actually another way of doing trip generation, which is called the cross classification model. And I want you to read on your own. It can be used for alternative for trip projection estimation. The approach assumes that, if you have a 3-member, 1-car household, you have like an average number of trips that you're going to produce. So we assume that all certain types of household will behave in a certain manner, whether or not they're from the same TAZs. So you could basically, this cross classification model can be used only for trip generation or trip productions. Trip production. Trip attractions are always estimated using the regression equation. But for trip productions, you can use this cross classification approach. And I want you to read section 4.2.3 to get the hold of this approach. So some of the comparison cross classification models generated for home and trip generation, typically for production. Regression models are for non-home and trip generation. The dependent variable is trip per person related with autos owned, household size. So this is, if you want to get a sense of that, then look at the example 4.3 in your textbook. And then regression model trip generation rates for both work and other trips ends can be developed using regression models. And you could also relate them with employment type and population characteristics, as you saw in that example problem. But again, we are focusing more on regression model. I do have an example by Dr. Kimberly Mastico that I posted online. So you should be looking at that on Canvas as well. So once you've done the trip generations, once you've figured out how many trips are getting generated by one zone, now our job is to sort of divide those trip generation into different zones, like where the aggregate trips are going to, and if you're basically estimating total attractions from your trip generation steps, then where those trips are coming from. So now, instead of just doing this one subscript where you're estimating TIs, you're now basically creating pair TIJ, where the first subscript represents origin, the second subscript destination. Okay, so this is sort of I represents the origin zone, J represents the destination zone, where PI, PI is the production of zone I, so total production. So this is going to be your output. So this is typically the output of your trip generation step. These purple things, this is going to be the output of your trip generation step as well. Okay, so PI and AJ. So these purple boxes are output of the trip generation step. So the previous step that we did, we get those as your output. This is the total number of trips being produced in zone I. And then this is AJ is the total number of trips attracted to zone J. And you can figure out TIJ. Now, intrazonal trips don't always have to be 0. I will specify if they have to assume them to be 0. So sometimes in some examples, there might be a TII, like for example, zone 1 to zone 1, there might be some trips like that, but sometimes there may not be, okay? And then this FIJ is what we call the friction factor that defines how separated zone I and zone J are. So think about it this way, okay? We apply, if you recall from physics a little bit, you have what we call, the gravity model. So I'm going to come and have that discussion. But this basically, what this equation is telling you is that two zones will have a lot of trips between them if they have a lot of production at zone I and a lot of attraction at zone J. Okay, so for example, Cal Poly attracts a lot of trips in the morning peak hour because we are a big employment center here at Cal Poly. So during the morning peak hour, our AJ value is pretty high. The number of trips attracted to Cal Poly. And where do those trips come from? The trips will come from very large towns. So San Luis Obispo is a relatively large town in this county, although it's a small town overall, only $45,000. Only 45,000 people here. But San Luis Obispo is a pretty large town for this particular region. Santa Maria is an even bigger town, right? But which zone do you think? Is it the city of Santa Maria or city of San Luis Obispo that sends out more trips to San Luis? The question is sort of up in the air because Santa Maria is 3 times the size of San Luis Obispo, pretty much, maybe 2.5 times at least. That it has that much population, but it's way far from Cal Poly. So this Fij represents a friction factor, and then you divide the number of trips between zone in proportion to that friction factor. And I have an example problem that tells you how you can apply this, a formula that you should do, that you should review. But Fij is defined as a constant times, the friction factor is defined as constant times the travel time. So this small Tij, small t, represents the travel time between zone I and zone J raised to power B. Raised to power B is basically how sensitive to travel time your productions and interactions are. Okay. Sometimes we call Fij a friction factor. Sometimes we call it a travel time factor, and we use that. The greater the separation between an origin and destination, the less likely, not impossible, but less likely the trip. So if you're talking about zones that are located way far from each other, you're not going to see a lot of trips exchanging between those zones. And then you also learn that the larger the two places, the greater the interaction. So the model from physics that we use for this is the gravity model. Remember what is the gravity model? Gravity model was the shorter the distance between the two objects and the greater the mass of either or both objects, the greater the gravitational pull between the objects. So this, the thickness of the line represents the gravitational pull. So if you have two large objects located nearby, they will have a pretty large pull. But then if you have locations that are far, then they will not have as much pull. These two zones are located pretty close, so they have a lot of pulls, a lot of trips between. So if you think of it that way, a lot of trips are going to be made between these two zones, for example. Propose a form of a friction factor. Fij is a constant time travel time. So travel time is a good way of thinking about what is the friction between the two locations. How far are they located? The travel time is large, you're going to have fewer trips. So convert the productions and attractions. Again, those are, you remember, those are the outputs. So productions and attractions, those are your outputs from the trip generation model. Output from your trip generation models. And then what you're doing is you're taking those outputs and you're converting them into what we call the trip interchanges, Tij. You're distributing the total attractions and total productions into different trips. Tij is the number of trips that go from zone I to zone J. Fij, a function of separation between the zones. How do you estimate that? And then I solved example 4.5 and I posted that video online on your Canvas page. And I'll also link a video, that same video on the comments of this YouTube video as well. So go ahead and watch that and make sure that you understand all of that. There will be a homework problem and an exam problem on this as well. So once you've done trip distribution, the next step is to do trip of mode choice. So this is the distribution of modal choice in the United States for work trips. And you could see that the number of trips being made as a driver is 69.1%, pretty large fraction of trips. And then all the other trips, like maybe as a passenger, and then different modes like bus, taxi, motorcycle, school bus, walk, bike, all of these trips are somewhat minor fraction. Does this pic look familiar to you? I don't know if you guys maybe are too young to have played Pac-Man. Pac-Man is a old style computer game that we used to play when we were kids on a computer back in the late 80s, early 90s. And that's what Pac-Man looked like. It's basically, you could see the drive alone mode is sort of eating up all the rest of the modes here. But anyway, how do we determine what mode people choose, right? So that's what this step of the travel demand modeling is about. Like once you've decided how many trips from zone I are going to zone J, you basically look at the different characteristics of the mode choices available to people. And based on that, you decide what is the probability of people choosing a certain route. So let's look at that. How we do this. What affects choice of mode? It's the travel time to access the mode. For example, if you're, if you're taking the bus, how much time does it take to actually get to the bus stop? Wait time, function of headways of transit vehicle, like how quickly does the bus come? Does the bus come 15 minutes or does it come every hour? If it comes every hour, you're less likely to take the bus because then, it's not going to provide you with the flexibility of your arrival time. So that's going to be an issue. So headways of transit vehicles. If there is a shorter headway, you're more likely to take transit. Transfer time, if you have to exchange the buses, what's the fare? How much time, how much money is going to cost you out of pocket. If you're going to drive your own car, what's the parking cost at the destination? For example, if you're talking New York City, or if you're talking about San Francisco downtown, we'll have higher cost. Tolls basically add, the out-of-pocket cost as well. You should account for this as well. And this alternative specific constant, it's kind of weird to read it like that, but this basically accounts for all sort of the intangible factors that go into a mode choice. For example, if you're driving your own vehicle, for example, your own personal bike or your own personal car, that gives you a certain type of freedom, right? You can leave and start whenever you want. And that has some value. And sometimes that could be hard to express in terms of the model. And that usually gets reflected in what we call the alternative specific constant in a model. So it's typically represented by like an A naught or A, simply an A, like it's sort of the intercept term in a model. And you'll be provided, I'll provide you with that value in example problems or in homework problems. But that's something that we are sort of trying to capture the intangibles of taking a particular mode. And then other qualitative data, like, if you have sidewalks, if you have bus shelters, things like that, sometimes that gets represented in the model. Sometimes that becomes part of the alternative specific constant. It just depends on how the modeling is done. And again, for the purposes of this class, we are not actually going to do any modeling. All we are going to do is sort of apply the models that will be given to us. So typically, forecasters use a discrete choice model where you are given distinct choices like bus versus car versus train, for example. And then for all three modes, you estimate, what is the likelihood of using that particular mode. Logit is a popular version of the mode choice model. And Daniel McFadden won the Nobel Prize in economics for developing the Logit model to get the mode choice estimation done for the San Francisco BART, SF BART, Bay Area Rapid Transit, San Francisco Bay Area Rapid Transit. So he applied that application of Logit model to forecasting for the BART rail system. So this was kind of an interesting tidbit about the mode choice model that typically, in transportation planning, you're not winning Nobel Prizes, but Daniel McFadden did win for this particular work. He won the Nobel Prize in economics. So this is something interesting trivia here. So what does the Logit model look like? We estimate what we call the VM, which is and sometimes it's called UM as well. Different representative variables may be used, but VM or UM or whatever, it's the measurable utility. And once you have the measurable utility of a mode, you can apply the probability of choosing a mode looks like e raised to power VM, it's the EXP, the exponential variable. So e raised to power Vm divided by summation of e raised to power V for all the modes that you're choosing between. Okay. So example 4.11, I posted a similar example as a YouTube video. So I'm going to link to that on this YouTube video, and it's also posted on your Canvas. So look at that. And then you could also look at example 4.14 in your textbook. So make sure that you're doing that. And then you'll have some homework problem that kind of applies this example. So what you're trying to get is the PM. It's the probability that individual will choose mode M from a specified set of alternatives. And typically you'll have 2 or 3 alternatives. So P1, PM might be P auto, choosing your own automobile, P bus or P train, for example, different modes that might be out there. And among those 3 modes, what probability you're going to have. Typically, you have P1, P2, P3, 3 different modes. The probability of choosing one of those modes will be, you can estimate that e raised to power the utility function divided by summation of all, for all modes, the e raised to power Vm, you just sum them up. And you could probably see that if you add up all the probabilities, they will add up to 1. Now you could use, let's say you did all this work and then your P1 particular probability of choosing auto mode came out to be, let's just say 0.72, and P bus mode came out to be 0.19, and P bike came out to be, bicycle came out to be, just an example, equal to 0.09. Right? You will see that without accounting for rounding, these should all add up. These 3 probabilities should add up to 1. Now, what you can also do with these probabilities, the probability of taking the car is 0.72, 72% chance that you'll take the auto. So if you're given total number of trips, let's say 1,000, you can convert 1,000 trips into different modes. So that means 720 trips will be using car, 190 trips will be using bus, and 90 trips will be using bike. So what you can do with these numbers, like once you establish the probabilities, you can convert those trips. And then same thing, if it was 2,000, you can multiply 2,000 by 0.72. And I hope you can see how I'm getting these numbers, right? I'm getting the total number of trips and I'm multiplying those with the probabilities. So if this was 2,000, I can get 2,000 multiplied by 0.72 to get the number of trips that are being made by automobile. 2,000 times 0.19, which will be about 380 trips. They will be made using bus, and so on and so forth. So you can apply those things, the probability values. Now, how do you actually get VM value? VM, you will be given equations, will be given in the problem to estimate VM values. And the utility value for each mode, you'll be given an equation, and you just have to plug the numbers into that equation. So make sure that you review the example video that I provided for an example problem, and review the example 4.14 from your textbook, and then 4.11 is provided in the example similar to 4.11 is discussed in one of the videos that I want to talk to you about, that I'm going to provide you on Canvas page. Okay. All right, let's go to the next step. Okay, so now that brings us to the last step of the travel demand modeling process, which is the route choice or trip assignment. Now, let's say you figured out that there is an origin zone, there is a destination zone, and you have 2 different links or 2 different routes that connect those origin and destination. How do you figure out which routes are going to people are going to use? Where do you assign these 1,000 trips between one route and the other? That's what we are trying to do in this, because again, one thing that is very important about the route choice model is that once you do your route choice for existing conditions, you can actually verify this. This is something pretty easy to verify because you can put tube counters on roads to figure out how many people are going to use that particular route for all OD pairs. And then you could see if your numbers are lining up. If your numbers are lining up, because you can easily count the traffic on a certain roadway link, if your numbers line up, that means you can be reasonably confident in your forecast. So that's why route choice step is so important, is that this can be used to verify your forecast that you're making, at least for current condition, your travel demand estimates that you're making. So typically, this is how the equation of travel time looks like. So the route people are going to use typically would be the one that takes less travel time. But the thing about travel time is that travel time is not just sort of a fixed value. Travel time also depends on how many other people are using the route that you're trying to use, right? So think about this. This is what the equation, or this is what the behavior of a link looks like. So let's say you have a route, and when the road is empty, it takes 1 minute to go from point A to point B on that route. If you go from origin to destination, it takes 1 minute to go there. Okay, so start point of a link to the end point of the other side of the link, it takes 1 minute. Now, initially, you can keep adding more and more traffic. So up to, in this, according to this chart, about 800 vehicles per hour. So this flow rate is measured in how many vehicles are using that link. So you can go up to 800 vehicles an hour. Your travel time won't budge. It'll still be the same thing, 1 minute, right? But as number of vehicles increase on that road, the travel time just goes up and up and up. And that's what we see. Like, travel time remains constant for a while. You can add 800 vehicles per hour, no problem. But as you increase the travel flow rate on that route, it's the number of vehicles using the route, the vehicle per hour, vehicle per lane per hour is the capacity. The travel time just increases. Once you hit capacity, the travel time increases even faster. Okay, so it's sort of an exponential curve. And a good sort of model for this is travel time equal to the initial T naught, like the free flow travel time. This is what we call the free flow travel time, the T naught. So I'm going to make sure you note that. The T naught is T0 is the free flow travel time. And free flow travel time basically is the travel time when there is nobody else using the road. And we know from practice that travel time can be that value even if you add a certain number of cars on the road, right? So the travel time remains fixed. But it's only when we reach the peak hour, the demand exceeds a certain value, is when the travel time starts to go up. So this exponential model of 0.15 flow divided by the capacity raised to power 4 is sort of a good model for travel time. And then this is the equation, what we call link performance function. Okay? Link performance function, it also used to be called volume delay function. But this is an old term that people generally don't tend to use anymore. So link performance function, or LPF, is what they prefer to use. Now, for the purposes of this class, to keep the calculation simple, I'm going to actually make your life easier and have a linear link performance function. So my link performance function won't be exponential like this, where you're dealing with raised to power 4 and stuff like that. We're going to keep the link performance function linear so that it's easy for you to solve equations and such. But something you should be aware of is that exponential function actually captures the link behavior much better, even though we don't use it for this particular class. Okay, now how we use the link performance function to divide traffic between different routes. Okay, we use two different approaches for that. One is the user equilibrium approach. The other is the system optimal approach. Okay, one is the user equilibrium approach and the other is system optimal. In user equilibrium approach, every user acts to minimize their own travel time. So when I say cost, so I'll sometimes use the term cost here. Okay, I'm using the term cost. And usually, typically, what we mean by cost is travel time. Okay, so I'm interested in travel time when I say cost. And everybody else doing the same thing. So to be able to minimize your travel time, what we figure the user equilibrium happens when a user cannot minimize their travel time any further by switching the route. Okay, so if I have two routes, okay, in that scenario, if I have two routes, and that's the only extent of the problems that we are going to solve in this class. If you're interested in sort of multi-route problem, look to take the CE 529 modeling and simulation class. And if you want to see the applications of these principles for tolling, how much toll we should put, the variable congestion pricing, you should take the CE 528 transportation economics and analysis class. So those will be interesting classes to take if you're interested in sort of application of this. But for now, we're just going to deal with two route problem. Okay, this two route problem and with linear link performance function. But the idea is that if you have two routes, I want to try to draw those routes. So if you have this origin and this destination, and then you have these two routes here. Okay, origin to destination. I have two routes. So this is route 1. This is route 1. And then this is route 2. So if I'm talking about user equilibrium will happen when the users have no incentive to switch between routes, when the travel time on both routes that are being used is exactly the same. If the travel time on one route is more than the other, what do you think will happen? All users that are coming into this OD pair, all users who are trying to go from this origin to this destination will keep taking the route that has lower travel time. But equilibrium will happen when there is no incentive to switch route. Both routes give you exactly the same travel time. And again, we are only going to deal with two route problem in this example, or in this class rather. And you will see that if you explicitly design a system where there is system optimality, then the aggregate system travel time is in fact lower, but the travel time, if everybody tries to minimize just their own travel time, the aggregate system travel costs are higher. Now, this might seem a little bit counterintuitive, but you could see this in a lot of different systems. Okay, so let's kind of work out an example. Typically, the ratio of system-wide travel time under user equilibrium and system optimal condition is what we call the price of anarchy. If people try to just minimize their own travel time, the system travel time does come out to be a little bit higher. UI plus UD, the aggregate system travel time under user equilibrium condition divided by system optimal condition is always more than 1. Okay, it's always more than 1. For a two-link network with linear LPFs, that's the kind of things that we're going to deal with. The price of anarchy is less than 4/3. Okay, so anywhere between 1 to 4/3 is the value. That's what we call the price of anarchy. Now, how can we estimate that? We can see that using an example. Now, okay. When we are trying to do this route choice or the traffic assignment problem, what we have to make sure is that we do a conservation of flow. Number of vehicles entering an intersection or link segment equals the number of vehicles exiting the exiting the same intersection, exiting that node. So So number of origins will have people starting at the destination. Sources and sinks is origins and destinations. There the number will be different, but then once you have any intermediate nodes, the number of people coming in will be the equal to the number of people going out. Okay, that's what we call the conservation of flow. Entering the back of the link equal to the number of exiting the front of the link over a long period of time. Again, you take a short period of time, there might be some storage in the link, but once the equilibrium is established, basically you have to have what we call the conservation of flow. So let's see. Okay, I want to pause here, and then I'm going to do this example problem in a new video.